All right, we're recording. So this is where we were last time, right? We were talking about oh, you can't see anything. Let's fix that. There, that's better. We're talking about setting up the language, and effectively what you do, because in Python you can give functions, like you can pass functions as arguments. We're taking the primitive set. We create a primitive set, and we have to say how many arguments any function being evolved is going to have. And then we say, well, what are the operators and what are like the terminals? Effectively, you're saying what are like the variables based on the length of this, right? If the length 7, it'll automatically be like, well, arg0, arg1, arg2, arg3, arg4. Like that's where you say how many variables are there. This is where we're saying what are the constants. And I'm allowing any integer between -10 and 10. I can't remember if randint is inclusive or exclusive, but that doesn't matter right now. And I add the functions, right? I'm going to add. It takes 2 operands. Sub, 2 operands. Mul, 2 operands. Protected divide, which we saw was a special one. Negation, it only takes 1 operand, but there we go. So this is where we're effectively telling the GP language, or sorry, the GP system what the language is. I want to be clear that this is not like what I just showed you is in no way am I suggesting this is a good or sufficient language for any particular problem. I'm just saying here's how you do it. Then we need to do a little bit of a setup. And this is kind of the magic code to do it. I'm creating something. When I put a string in here, this is just, and by the way, if you're like, well, explain that function to me. No, go read the docs. I'm not going to read the docs to you. But basically, I create something. I put in a string here. It's kind of like defining something for the system. It's a fitness, and the weight is -1. The reason it's -1 is it's a minimization problem. What's neat about DEAP is you'll notice this isn't a tuple. It's a tuple with only 1 element in it. That's important, actually. This needs to be a tuple, even if there's only 1 element. Because DEAP is designed to work with multi-objective problems. Sometimes you have something where you want to minimize several things, or maybe minimize some things and maximize other things for a single problem. Like if you did anyone in here do the delivery problem with like time windows or anything for assignment 1? No? Well, that would be an example of a multi-objective problem where basically you want to minimize the total distance while also minimizing the total number of like delivery vehicles that are also out, right? So what you would say in that particular problem is you could be like, well, -1, -1. There's 2 fitness values, they're both minimizing. But sometimes one of the metrics or one of the things we want to minimize is more important than the other. So that's why like we can have weights. If we want to be like, okay, minimize both things, but really focus on the total like distance. So the weight of that one would be bigger. It would have a bigger magnitude. We say, okay, what isn't it? Yes?
When you say bigger, do you mean bigger in terms of like a bigger negative number or a bigger
Magnitude, so like a bigger negative number, yeah. And if it was positive, a bigger number, yeah. What is an individual? Well, we're doing GP. It's going to be a primitive tree. And the fitness for this thing is going to be based on the fitness minimum. That's what this is. What this string is what this is going to effectively be. Okay? Then we create a toolbox. We tell how are we going to generate the tree. Well, when doing that, if you go read the documentation, it's going to give you a bit of an explanation. Remember, this string is just what we call it. This gen half and half, that is a style of generating a tree. I won't go into the details. That would be like if we were doing a course strictly on genetic programming, I'd get into something like that. What is the primitive set? It's the primitive set that we defined. The minimum height for the tree is 1 and the maximum height of the tree is 4. That's only for the generation of the tree when it's being created. We don't want the trees to get too big. Through evolution, they might get bigger, but for generation purposes. What is an individual? How are we going to generate an individual? Well, we say, okay, we're going to initialize iteratively based on the individual, which is defined up here, and we're going to generate them based on the generative tree. All of these details, again, are in the documentation. What is a population? Well, it's going to be a list of those individuals. How are we going to compile it? Well, with this thing that's already kind of predefined for us, gp.compile. And then we register our evaluate function. Well, what is the evaluation function? Well, mean squared error fitness that we defined up here somewhere. I guess I'll show it to you later. Oh yeah, I get to it right there. Mean squared error, what's the toolbox? Basically, this is the magic setup code. If you really want to know what every piece means, go look at the documentation. And then we also register how are we going to do selection? We're going to do tournament selection. How are we going to do crossover? Well, it's going to be a one-point crossover. How are we going to generate a mutated subtree? How are we going to do mutation? Yada, 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 yada. Okay, so that's just all the setup. We are defining things. You'll already, look, you've never done GP in practice, but you might be looking at this and being like, if all these things are already predefined, can I use this for a GA? Yes, you can implement a GA really freaking easy with DEAP. It's trivial. This isn't too bad either, don't get me wrong, it's just you've never really used DEAP before. All right, what does this code do? Well, I already went through that. So mean squared error, you'll see mean squared error fitness is how I define how are we going to do the evaluation. If we go up here and you'll look at this function that I defined, it's called mean squared error, not mean squared error fitness. So you might wonder what's going on, what's the deal? Well, first note that this function, all it does is take a compiled individual, and remember a compiled individual is GP is evolving trees, and we can't run a tree. We have to compile the tree into something that can be run. It effectively turns the tree into a callable function. So a compiled individual is effectively a callable function for it's the phenotype. It is a phenotype where the tree is the genotype. So this is a converted into the phenotype, something that we can actually call. So compiled individual, we get our independent variables and our dependent variables. Basically what we expect to get and all of the arguments that we want to give to our function. And how do we do it? We just loop over everything. We say take the compiled individual with all of the arguments, get y hat. Remember, y hat is what our function predicts. And we compare it to what we should get, and we do the mean squared error. So that's all this is doing, and you'll notice this returns the mean squared error. We add up all the squared errors, then we divide it by the length of the dependent variables, because that's the length of mean squared error. Any questions about this before we go to the next bit, the mean squared error fitness? The mean squared error fitness is effectively a wrapper function. The mean squared error is just mean squared error. It's a nice clean function. It's easy peasy. It doesn't really depend on anything deep. It's just a function. The closest it comes to depending on anything specifically related to DEAP is the fact that that one parameter was called compiled individual. Other than that, it's a function that takes a function and calculates the mean squared errors. That's it. So we need to make it work a little bit with DEAP. And you'll notice that the argument list here is a little bigger, our parameter list. An individual, a toolbox, independent variables, dependent variables. So here we get back it takes an individual and a toolbox, but up here it just takes it took the compiled individual. So what's going on? Well, first it does some error checking for exceptions. Is the independent variables, is the length 0 or is the dependent variable length 0? If it is, number of dependent and independent variables must be greater than 0. If the lengths of the variable lists are not the same size, something has gone wrong, we throw an exception. Otherwise, callable function, we say toolbox compile the individual. This, if we scroll up, this one here, I have that set up. That is the tree. This right here, toolbox.compile, that turns the tree into a callable function. Then we call mean squared error with the callable function. We get back the value. And then here we're returning. And you'll notice I made it a tuple. It's one value, but it has to be in a tuple. It has to be to make DEAP happy. It's just the way it is. I didn't make it that way. Somebody else did. Questions about that? It's simply a wrapper function to make DEAP a little happy and do some like error checking as well. Now, bloat control. Remember we talked about bloat and how bloat was a big problem with genetic programming systems. This is by no means sufficient to really eliminate bloat. Sorry, to even say really eliminate. This is by no means a way, like this will not eliminate bloat. Bloat is going to happen. It's a big problem with your genetic programming systems, or genetic programming in general. It just happens. There are some things we can do to hedge against it a little bit. And some of those things are, well, first of all, make sure the initial trees that you create aren't too big. I mean, don't start it off with really big trees that are going to grow that much faster, because it's a rapid growth. It's like an exponential growth, given the nature of like trees, right? But what do we say? Well, when we're doing mate, let's make sure that the height of our trees never exceeds a certain value. And when we're doing mutate, same thing. And you know, although the height of the tree and the number of nodes in the tree are obviously very related, we'll also say, let's limit the maximum number of nodes that we'll allow in our trees after the genetic operators have taken place. If your question is, how does it do it? Like, how does it actually enforce that? I'm not 100% sure. I don't remember. I read the documentation on this a couple years back. So if you're really curious how, by all means go have a look, but I couldn't tell you off the top of my head. Can anyone think, and we talked about it already, but I'm curious if, like, I'll give you a hint. Can anyone think of another way to indirectly reduce bloat in your genetic programming system? This would be a way you can, I realize the question I asked was very high level, but so let me try to make it a little bit more concrete. What can we do with our algorithm? I'll just explain it. What we could do, were you going to say something?
Yeah, I think I was, but I don't know if it's right or not.
What were you going to say?
I know that we talked about like saving functions themselves. So if you see like the same thing in multiple trees, can you just save that function?
That's interesting. Kind of like replace it with, yeah, something like that could totally be implemented, but I'm thinking of something even simpler. An easy way, and it works decently well, but it does come with some downsides. An easy way is you can count the number of nodes in your tree, and you know, this is a minimization problem. We're minimizing the mean squared error. But we could also minimize each individual's mean squared error and the number of nodes in the tree. Meaning, if I have two trees that give me similar, if not equal, fitness values, but one has fewer nodes in the tree, take that one. We actually add a selection pressure to the system to be inclined to pick trees that are more brief, that are shorter. And that's a good thing. Now this does come with some costs. I mean, you have to calculate it. Fortunately, I'm pretty, like, I don't know how it does it, if it's actually, like you can just say the length of the tree and it'll know how many nodes are in the tree. I don't know if that's calculated on the fly or if it's a stored value that gets updated every time the tree gets adjusted, but it must be calculated on the fly. But then there's also the problem of, you know, what's more important? A more correct, like an individual with a smaller mean squared error, or one that's briefer, like that has less nodes? Obviously, we want to maximize or minimize the mean squared error more, so we need to adjust the weights accordingly. But what should those weights be? Like obviously, I want to minimize mean squared error more than I want to minimize. If two individuals, one has a really great mean squared error and one has a really bad mean squared error, but the one with a really bad mean squared error is one node, I really shouldn't pick that by virtue of it being, oh, well, it's shorter, therefore it's better. Well, no, it's garbage. So, I have to kind of like choose and order what's more important. But how do I weight these things? It's tricky. Yeah.
Can you go through and like go until it kind of plateaus by just doing like mean squared error, and then set it so that it starts to look at the size?
Absolutely you could. Anything, like almost always, whenever the question is, could you? Yes. Why not? Try it, see what happens. There's only one way to know how much it would work. And it almost feels like, I've said this throughout the semester, like this is why I really like evolutionary computation is, it encourages you to be creative. Like with like your functionality, which you don't really get to be a lot, right? Like, when you think of like, this is so stupid, but like when you think of creative outlets, you don't really think about like writing code as your art, right? But like, it almost like enables that. Like you get to be creative. And you never really know how it's going to work out until you try it. And that's also another thing that's fun, especially when you get these algorithms that take a long time to run. You hit run, and you're like, I got to come back in an hour. But oh boy, when that hour is up, you're like, oh, let's see what we got. Oh, it's like Christmas. You get excited, or it's a lump of coal. I don't know. You get lucky, you get unlucky sometimes. So there's a lot of fun. I think this stuff is a lot of fun because it does encourage the creativity. And I think it encourages creativity a lot better than other forms of similar types of algorithms, like in the space of like computational intelligence. I think like this stuff is just asking for, here's the basic framework, do whatever you want. All right, bloat control. And then there's some bookkeeping stuff we can do. Like you can create like a hall of fame, which will always keep track of like, well, what was like the best number of individuals throughout evolution for each generation. You can create these like statistics thing, like, well, the fitness, the size, the height. We can create this like multi-stat tool to keep track of all these things, and we can register, well, how are we going to calculate these things? And then in the end, you can print out the results. And it'll kind of like print out like a table of like each generation. What was the average mean squared error? What was the standard deviation, the minimum and the maximum of the various, of the fitness, size, and height? You'll see an example printout in a moment. Running in results. After all that's set up, I can do something like this. I create my population by calling the toolbox population that I defined earlier. If you're like, okay, toolbox population, what's that? Well, we define that up here somewhere, I think, right here. If we called this here like PPL, down here I would have to call it PPL, just to be clear. Whatever you put in the string, it kind of goes and makes like this like method for you, or function, I guess, I don't know. Toolbox, was it? I think it was an object. Population, log, this returns the log and the population after you're done. This goes and evolves for some number of generations. When it's done, it returns the final population. And the log book, that like bookkeeping stuff. This is how I call it. Now I want to be very clear. On your assignment, your ability to like do anything interesting, like if you call it like this, where you say like algorithm.ea simple, if you call it like this, you're not going to really have a lot of options to do anything interesting. You kind of have to, there's a way to call each individual bit, as like we were talking about, where like you kind of define like, okay, call your selection, call your genetic operators, call your fitness evaluation. Like you define that like generational loop yourself. You don't call it like this. You're going to want to do it that way in order to actually do anything interesting in the assignment, but this is the quick and dirty way to get something running. And with the above settings, I hit run, I print out like the log book. This is what gets displayed in the end. So we've got, you kind of see like it's showing like the average, the generation, the max, min, The table kind of get messed up with tabs. Any val, standard deviation, average, and it does it for each of the three things that we defined up here: fitness, height, and size. Okay? And these are the things I'm measuring. And it produces this table. I ran this for 100 generations. In the end, I did not include those because this table would be really big. But we can see, like, this is what we get in the end. It's kind of nice. Yeah? Yeah, I think so too. So that's an example of using DEAP. And if you want to get the best result, okay, I can get the string version of the Hall of Fame. This is, by the way, it's very important. If you ever print out an individual in DEAP, it's going to be like Python garbage. It's just going to be all this like object crap. You have to convert it to a string. When you convert it to a string and then you print it out, you actually see what, like it'll print like this nested S expression, which means the negation of adding 1 to argument 0. That's like the crap GP does. Well, what happens if you negate a negation? Well, that's just, you just undid it. So really, it looks like after evolution, my genetic programming system where this was my data, it looks like the best solution I could find is just 1 plus arg. What was it? 1 plus arg 1 was it? What was it? One plus arg 0. And that was its mean squared error. That's actually not too bad, right? Now, I don't know how right that is. 1 plus arg 0. If I ran it longer, maybe I'd get a slightly better result. Maybe I can get a better mean squared error fitness. But hey, we're kind of there. Yeah, so given the above, yeah, this is what I would simplify it as, x plus 1. The mean squared error of the model when applied to all the data is roughly 0.00906. That's the squared error. Okay, any questions about what we see? All I'm showing you is like, oh, this is kind of how you set it up. Follow through this when working on the assignment and the documentation, and you'll get it working just fine. Funny results. Given the stochastic nature of like the search, every time you hit run, you're going to get, especially like if you're dealing with floating point numbers, you're going to get different results every time. And since genetic programming's goal is to fit the data, it doesn't attempt to simplify anything. No, there's no simplification process in your genetic programming. When you get a final result, most of the time you got to look at it and kind of like, okay, what does this mean? In like that example right there. Negate, add 1 and arg 0. Okay, well, what does that mean? Well, like I said down here, well, that's like x plus 1. That's just x plus 1. I had to simplify that. And genetic programming will do things like this. Like these are actual results I got here. Subtract, like what is that? Okay, protect the divide. Arg 0, that's effectively like x, okay? X divided by negative x. Well, that's negative 1. And then subtract x minus negative 1. X plus 1. I had to simplify it. What do we have here? Add the multiplication of the protected divide of that and the protected divide of that and arg 1. Like, well, what's going on here? So multiply 1 by, okay, this is 1, that's 1. Multiply 1 by 1, that's 1. Add 1 to arg 0. Okay, cool. Like, we have to simplify it. All of these things, like look at this one. Add negative 8 to the addition of x plus 9, x plus 1. It's all the same. But we have to simplify. And sometimes you get rather silly ones too. Like look at this one. It just keeps going. Now in this particular example, one could imagine, like these are actually all evaluating to literally the exact same thing, x plus 1. If I included in my GP system some selection pressure towards smaller functions, like smaller trees, some of this nonsense would probably have died out in the evolutionary process. Cool? Thoughts, concerns, comments, anything? So this was a bit of a tutorial on that. And now, for the sake of time, because as of now, let me do a quick calculation. As of now, what I'm probably going to do, only 2 people wanted to do a presentation, you and you. That's awesome. Because only 2 people want to do it. Now, let me ask you right now. I suppose it's up to you. I know when you're not used to doing like presentations, you might think, oh, I don't want a lot of time. Trust me, you do. Okay? So what I'll do, you don't have to use the whole time. So what I'm thinking I'm going to do, because both of you want to do it, you'll both get a whole lecture to do your presentation. You can make it, you don't have to take the full 50 minutes, but you'd be surprised. Every time I tell people for their lecture, no more than 20 minutes, they'll all go 30 without even trying. Like, it's so common, okay? So if you're, oh, how will I fill 50 minutes? First of all, you don't have to. Chances are you will. So I'll give you a full lecture. Last day of class is the 6th, right? So let's call it that week. And then we have 8 people that are doing lectures. So that's a total of, if I do 2 lectures a day, that's a total of 4 days. 1, 2, 3. So we can do that. And then, yeah, we're running. So because of that, we're going to skip this topic. This topic was, let's all play with genetic programming. We don't need to do that. You've got your assignments. You're fine. So we won't really work that. If you really are like, no, I really want to do this, then do this on your own. You're fine. There's nothing more I can do here that you can't just kind of do on your own. So for the sake of time, I will move on. Cool? Any questions or anything? Yeah.
For presenting the final project, when is this typically going to get released for that?
What I'll do is you're basically going to be in the last week. So I don't know. Do you want to go before him or do you want to go before her? What do you want?
I just don't want it to be on December 4th.
You don't want. What's December 4th?
Well, the 3rd's X-ray.
Yeah, same actually.
So I just don't want to be on the 4th. That's it.
Well, in that case,
That.
okay, hold on. So
And we don't have
That's
classes.
on Tuesday.
we don't have classes that Tuesday?
No, because it's X-ray.
It's the feast
I
of
mean,
St.
I-
Francis.
Yeah.
So you're telling me, hold on, you're telling me that, so effectively we actually have 2 days that week to do lectures, but one of those days you both really don't want to do a lecture. All right. Well, I'll have to think about that. Who, do you have a preference on, like, do you want to go before her or do you not give a shit? Or how about you? Do you want to go before? You don't give a shit.
We probably split a lecture.
Yeah, but that only gives you 25 minutes each. And I'm willing to bet you could easily go more than 25 minutes each without even trying. Because think about this, right? Whenever you're giving a presentation, like here, if
I could do the 4th.
look, I'm willing to be flexible.
I could do the 4th. Or I could.
Yeah, but are you going to be in rough shape? Let's see, okay. Let me give you a point here. I think down here I have an example. So think about like this. Okay, of course. Whenever you're like presenting stuff like this, like when I'm starting to explain a problem, it could take a long time to explain a problem. Because there's a lot of background information you got to know before I can even talk about like how am I going to apply an evolutionary algorithm to this. So that actually takes a long time to explain. If you think I'm going to if I'm going to stand up here and talk 2 minutes about fMRI and explain that to you so you can understand what I'm doing with genetic programming, no, that ain't going to happen. You're going to take a long time to talk about that. And like, in fact, I'm being nice to you to allow you to go that long. If I go to a conference, they'll give you 20 minutes. And you say, but I need more. They go, nope. And if you try to talk for more, they'll cut you off. Like, it's hard to be brief. So you explain the problem. you explain the data, because, okay, understanding the problem is one thing. Now you have to understand the data and how it's going to be remotely relevant to your evolutionary algorithm. Then you got to explain, so what are you going to do? What did you do with your evolutionary algorithm? So you got to explain all of that. That takes a while. And if you do anything interesting, there's a lot to explain. Then you got to talk about the results you got. Then you got to talk about what it all means and like what you could do further. So all of that, like I know you might be like, yeah, okay, well that's just a typical presentation. But when you're explaining something that you did and you figured out everything along the way, it takes a long time to explain that all. It takes a lot of skill to explain it all in a short period of time. And I mean this in the nicest way. You're not that good yet. Okay? So you're going to need the time. And that's okay. So I really don't think, so I'm going to have to think about that last week of class.
I could do the 4th. It would be fine.
Okay, we'll see. We'll see. You'll take one for the team? So that means you'll do the 5th or the 6th or whatever. All right. Because the 6th is the last day of lecture, right? Wait. Is the last day a Friday?
Yeah.
Is it actually?
Oh.
Okay. 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 Remember last year, everyone was so confused. What was confusing about what we did last year? That made perfect sense to me. Anyone who was, remember last year they did that thing where like, okay, look, we missed like 6 Mondays, so the last 2 days are Monday schedules. Okay, and everyone's like, I'm so confused. How? How dumb do you have to be if that confuses you? It's a Tuesday, but we're pretending it's Monday? Like, give me a break.
Class is Friday.
It is, and it is a Friday. Friday. Okay. All right, so one would assume. Okay. All right. Okay, let me just make sure there's nothing in here I'm missing. Okay, run on multiple instances. Total of 20 instances are made. Yes, so, and this is like what you do on the assignment, is there's data I give you. I give you magic tables of data, and we play a game. What are the functions? You tell me. I got your data. You have to tell me what were the functions that I used to generate the data. So you have to play this like reverse game, which is kind of fun. Okay, the language, define the language. Multi-objective problems, okay, this is me just saying a strategy for managing bloat is to also add a minimization of, a minimization of the tree size. Cool? Cool. All right, tuning hyperparameters. All evolutionary algorithms have a lot of hyperparameters. Some have more than others, and one of the common criticisms of evolutionary algorithms, although most forms of similar types of algorithms have a lot of these things that need to be tuned, there's a lot of things that we need to play around with the hyperparameters. And you might remember too, there's like the actual numerical hyperparameters, those things that like we've got like dials to change, but there's also the fact that I can change out what crossover I'm using. These are things that I can have control over and I can play around with. So there's a lot of playing around we can do with our algorithms. And like it or not, here's the right way to do it. There is no such thing. You just kind of hack around until you find it. There are some automated strategies for this type of stuff for some types of algorithms, but in general, they're not great. Really, the only strategy I suggest is put in some numbers, hit run, how'd it look? Change them, hit run, how'd it look? And you kind of play that game a little bit until you, as a person, kind of converge on like, okay, I'm getting good results, I'm happy with them, let's go. You never really, like this is the magic word you use. Whenever you go and you're writing up your research, if you're doing this type of stuff, if you don't explain how you tuned your hyperparameters, people are going to be like, what'd you do? How'd you do it? How'd you decide these hyperparameters? But if you say the magic word, if you say the magic sentence, hyperparameters were determined empirically, everyone's like, oh, okay, that's fine. All you have to do is say, yeah, I played around, I found something that worked, and we're good to go. I'm making no claim that these are the best hyperparameters out there for this particular problem. I'm just saying I played around with them enough that I was sufficiently happy with the results I was getting. That's the magic word. Everyone knows that searching for the best hyperparameter is a fool's errand. It ain't going to work because it's always that game of as you're finding the right number of generations, it changes what the right number of population size is, which changes how you should do your selection, which changes how you should do your genetic. They're all so interconnected, you can't find the best. There's no such thing.
When it comes to like the generational hyperparameter, what is like why is that a hyperparameter instead of something that you can just look at the difference like between like the last like X amount of time?
Well, that's what a lot of people do. Is when do you end evolution? That's like one of the first things we talked about. When do you end? Termination. When do you end? Do you end after the population seemingly converges? Do you end after you hit a threshold? Like after I find a result that's sufficiently good, I'm happy. Do you end after some amount of diversity based on some arbitrary metric you come up with is like that threshold is met? Or do you end after some predefined number of generations? All of those things are valid and fine. I just tend to go with the number of it's the easiest. And it tends to be easy to, especially when learning this stuff, it tends to be easy where I'm like, make that number bigger. Oh, make it smaller. Oh, right? And you might be surprised. Sometimes it's so common to see your curve go like this. Right? And so you never really know when to stop. You don't. So whenever you check for a convergence, like, yeah, that's fine, but like everything in this space, you can do it. You don't really know. A lot of times people too, what they'll do is they'll do mating events as some way to kind of standardize things across, whether it's generational or continuous, or to kind of like the population size and generations. What they'll do is mating events. Well, they'll count the number of mating events that happened. So if you crank up the population, the generations, basically, like if you have a bigger population, you will have more mating events earlier than you did if it was a smaller pop. So it's kind of a way to control for that. I don't really recommend that particular way. I think it gives you less control. And I'm not clear why it really, what you're doing to make it more fair. If your goal is to find the best result, what do I care? But anyways. Okay, symbolic versus numeric hyperparameters. Symbolic hyperparameters are like those modular options we have. What crossover operators are we going to use? What selection operations, mutations, etc. These are decisions. These are like those big like modular boxes that we can take out of our algorithm and put in a new box. And then there's the numerical ones, which those are like, well, I've got tournament selection in here. So there's like a box. Like think of your algorithm as like, oh, I've got this here, and that's connected to this here, which is connected to this here. And then this is the selection I'm using, and the selection, yeah, and then, oh, I want to change out the crossover, so I'm going to go and just remove this box and put this box here, and that's, okay, there, it still works, because they're all designed to work, like it's like plug and play, right? But depending on the box, you might have different dials. Right? That I can, oh, okay, well, depending on I can turn these dials however I want. So the symbolic hyperparameters, those are like the modules themselves, where the numeric operators, those are the dials attached to the modules. So regardless of the hyperparameter type, their value needs to be set. Crossover needs to be set. Which selection are we going to be using? Symbolic hyperparameters may introduce new numerical hyperparameters, like I was just saying, depending on the dials that I can turn here. The numerical hyperparameters are the low-level ones. They're more like, okay, I'm doing selection, tournament selection, what's K? Where the more abstract, high-level things are like, well, how am I going to do selection? Right? So there is a bit of a level to it, although I would say be careful of making like sweeping statements. But like in general, that's how we think about these things. An evolutionary computation algorithm instance. Now, This is weird, but this terminology is somewhat important. So an evolutionary computation algorithm instance, or just like the instance of the algorithm, is the one that has all of the hyperparameters set. Okay? A genetic algorithm is a genetic algorithm. A genetic algorithm with all of the selections and everything and all the settings set, that's an instance of a genetic algorithm. There is no correct way to find hyperparameters, but usually you start with like good starting values that are common, and then you just kind of go from there. You hit run, you hit run, you hit run, you hit run, until you find something you're sufficiently happy with. But that begs the question, where do you start? Well, there is no correct way to go. This is really, you just kind of get a feel for it. You kind of get a feel, you're like, I'm doing TSP, and it's a pretty big instance, so I know I'm going to want settings around this value. And then it's tricky, because if you ask me like, well, why? I go, I don't know, I just got this feeling. Like, that's the best I got, because there's no right way to do it. There are some, like, okay, a great starting point for crossover is a crossover rate of 80 and a mutation rate of 20. If this is like a genetic algorithm, if this is like genetic programming, you typically want mutation to be way lower, like 5% tops. But everything's tunable. If you need to crank it up higher, great. But yeah, for genetic algorithms, this is probably the biggest, most like common standard starting place, I'd say. Everything else is kind of like, eh. Yeah, okay, for genetic programming, 20% shockingly high. Some symbolic hyperparameters choices may be numerical hyperparameters that need to be set. For example, tournament selection requires a tournament size. Yeah, for population size and number of generations, it's difficult to say. It really depends on the problem and the instance of the problem. 1,000 generations might be enough. Maybe 10,000, 100,000, I don't know. You just got to try it and see what happens. Some hyperparameters, and this is what I was saying a moment ago. As soon as you're like, okay, all right, now I'm going to be testing the number of generations. Okay, great, I'm happy with it. Now how about the population? Okay, I'm going to tune the population until I'm happy. Okay, great. Well, you probably have to go back and double check your number of generations. Maybe it can go bigger now or less because of the number of, like, the population size. You don't know. These all impact each other. As soon as you change one, you probably need to go update the other. So it's a bit of a game that you really just have to have a feel for. And then you just do your empirical tinkering. Once the hyperparameters are set, algorithms should be run to get a sense of the performance. Based on the performance, values need to be adjusted. So if I have a hyperparameter that I can tune, it's a numerical one, and it looks something like this. Oh, if I make it smaller, I get better results. Okay, great. Do it, right? But, of course, there's times where, well, let's change the... I'm trying to think of one that really wouldn't be relevant. But let's say there's one that's not that relevant. No matter what you change, it doesn't really have that much of an impact. Maybe it's population size. I keep making it bigger, and it doesn't really make much of a difference, actually, for my particular problem. So, okay, let's pick something I'm happy with there. But again, just as soon as you make a decision here, going here, this might look wildly different. Is that clear? Yeah. So the difficulty here is that the hyperparameters have complex interactions. And when I say complex, I mean like this is like a well-defined idea. Their interactions are complex. It's a complex system. Everything's so interconnected that like you can't tease anything out. Nothing makes sense. Increased population size may require an increased tournament size. Increasing mutation rate may require more generations. Suddenly, the crossover rate matters once mutation rate grew past a certain criteria. You don't know until you try and get your hands dirty until you're playing around. And to make matters worse, good hyperparameter settings are highly dependent on not only the problem you're studying, but individual instances of the problem. So it's not just like, oh, TSP versus graph coloring. It's this TSP instance versus that TSP instance. Just because you have a good set of hyperparameters that worked for one mean nothing for the other one. In other words, Yeah. Don't go looking for the best configuration. That's a fool's errand. It's not going to happen. There's literally an uncountable infinite number of configurations. You're not going to be able to do it. The trick is you just play around. So on assignment 1, would you agree? Yeah, you just kind of had to hack around until you found settings that work. Of course, right? Who here has been working on assignment 2? So you just kind of have to hack around until it worked, right? You just keep playing around until you get something that works. Yeah. With experience, this process gets easier. I don't know if it gets easier because you really get it or because you get such a sense of how futile it is that you just don't give a shit anymore and you're like, good enough. But be aware that don't get too stuck into optimizing those hyperparameters. Good, great, good. Don't get me wrong. Awesome, you're learning. That's great. But it is a fool's errand. You're never going to find the best, so just make yourself happy. There are automated systems to figure it out. They all suck. Don't waste your time. Maybe one day they'll have a good one, but they're not great. And a lot of these systems aren't really designed for like big algorithms like evolutionary algorithms anyways. They're more like systematic ways for doing like cross-validation for like k-nearest neighbors or something. Any questions about that? Long story short, hack around. But, okay, so this is where we'll end it. I set my hyperparameters, and I'm really happy with the results. And maybe I want to say my comparison is one algorithm versus another algorithm, one instance versus another instance of a genetic algorithm. Which one's better? And how do I really find out what's better? Well, that's what we'll talk about tomorrow.